Okay, it's time for the vector, or what is known as the cross product, for us to have a look at that. So the distinction here between the vector and the dot product is a scalar, just gives a numerical value, gives a combined distance in a given direction, in the same direction. The vector product gives a vector. Now, the vector, let's have a look at an example. Okay, so if the dot product works so that it looks at the parallel combination of two vectors, and you remember how that was done, A would be projected onto B like so, and we'd take this bit here of A and multiply it by B, and we'd have the dot product, which was AB times cos theta. Now, that's all well and good, and that's actually the dot product. Importantly, works for any dimension. So you can get the dot product in 2, 3, 4 dimensions. The cross product only relevant for 3 dimensions, only relevant for 3D. So we're not gonna. What we're looking at now is finding a vector that represents the perpendicular combination of two vectors that is perpendicular to them. So let me explain. So here's A and here's B. If we looked at, if this was this here, so maybe I can be a little bit neater with this. So I'll get my ruler out and I will line this up so that we're getting a nice perpendicular line there. And okay, so what we have there is a projection that's 86 degrees. I'm going to bring the same angle up over here, and okay, so this maybe, yeah, okay, this angle, so here's the angle theta between the two vectors. These two vectors are in two-dimensional space. This is a right angle, and this value here, this distance here is a cos theta. Right, that's to here and here. So we know that the dot product, oh, that's a dodgy line. The dot product was a magnitude of A cos theta by the magnitude of B. That would give us the dot product. Now, what we want to do is the opposite of this now. We want to have a look at the part of A that is perpendicular to B. So that distance is this one here. Now, this distance is not A cos theta, but A sine theta. That's that distance there. So that's the part of A that's perpendicular to B, and so therefore what we call the cross product, or A times B, we say that A times B is equal to, well, it's A sine theta by the magnitude of B, or if you like, A B sine theta. Now that's the cross product of A and B. It's not a vector though. That's still a quantity. That's a value. So this, what we've got there is that's the magnitude of A cross B. A cross B itself is a vector. A cross B is equal to all this. Right, this is just a value, and importantly, multiplied by the normal vector, the vector that is orthogonal to A and B, that is perpendicular to both of them. So that is the unit normal vector. That's the unit normal vector. So what that does is it doesn't affect the distance or the magnitude of our vector. It just pushes it into a certain direction. So AB, if it goes around, so A cross B, that's going to push. So what we've got here, we're going to have a vector that, if you can imagine A and B on a plane, then and this blue dotted line popping out there, that's that's coming out of the plane, this one here, that's orthogonal to A and B, but there's another one down here, isn't there? So I might just get my ruler out again, and we could be going back through the page underneath like this, and that's actually the one that we've got. All right, that's our n. That's our normal vector there. Now I know that because this is A cross B, and we're going in this direction. Anything that goes in this direction, from left to right, if you like, there is a right-hand rule that I could try and explain to you. It's very difficult through this medium. Oh, I'll just drop my stylus. But so it might be easier to talk about anything that comes this way gives us a negative value, so a negative cross product, and will result in a normal vector that is disappearing down. If we went with B cross A, and so this is something to note, that it's not commutative, cross products are not commutative, B cross A would be popping up out of the page and up in a positive direction. So there are a couple of points to note there. So that's our unit normal vector. The magnitude of the cross product is just AB sine theta, and that's in a nutshell our cross product. Now, if our vectors A and B cross to 0. Now, if you remember, for a dot product, if A and B cross to 0, I'll just make this note over here. If A times B equals 0, so with the dot product, what that meant is they had no parallelness, which meant they were perpendicular. Now, because we're in the cross product, we're measuring perpendicularness, then it's the opposite. If there's no perpendicularness, they must be parallel or they must be collinear. So if A cross B equals 0, then A and B are collinear. The vectors are collinear. Then A, B are collinear. Okay, so the other very important point we just mentioned there, I want to make sure we get all this, that A times B cross B, is not equal to B cross A. And what we discovered was it's the negative of. So we can write a bit more specifically that A times B is equal to the negative of B times cross A. Okay, something else here about the cross product that's quite useful. If I pick up that vector A and reproduce it here so that my tail is on the tip of my B vector, which I don't think I've actually achieved, have I? Excuse me. I think I need to move that along a little bit. So I pick it up so that it's in line with my B vector. Sorry, there we are. So if I just reproduce my A vector there, I think that's about the right length. And if I do the same over here for my B vector, so at 4 degrees. Haven't done too badly there. Then what we have is a parallelogram, and what we know about parallelograms is that the area of the parallelogram that results here with my A vector and B vector is, well, we know the area is height times base, don't we? And our height here is A sine theta, and my base is B. So that would be A B sine theta, which we have just discovered to be the magnitude of my cross product. So that's quite nice. And in fact, we can add to that, and if we have if we join up perhaps our tail of A with B, just down here, then we will be able to add that the area of this triangle in here will be equal to 1/2 of my magnitude of A cross B. So this is all going to be really useful when it comes to finding areas and using our cross product. So let's just see, how do we calculate the cross product? So let's have a look at an example. Just be a fairly straightforward example. So I'm just going to pull one out of my hat. So let's find, remember, only in 3 dimensions does this have any sort of meaning. So find, so for the vectors, let's say 3, 1, negative 2, I'll give that a name, A, and B, which will give 2, 3, negative 1, find A cross B. So find the cross product, the vector product. So the result's going to be a vector. So how do we do it? Okay, it's quite a complicated process, although once you get it, it's all right, but it's not intuitive. So A times B, so this is how we do it. So A times B is, so therefore A times B. What we're going to get is a 3x1 vector. All right, and the components of it are going to be found like so. We're going to go in a row by row manner, and we're going to do it in this way. And if I'm going to repeat, I'm just going to rewrite these vectors down here so that I can show you how it is done. All right, so we're taking this vector. In fact, I don't know why I just don't rewrite it there. Okay, so we start by ruling out the top row. So we're just going to rule out the top row, not going to include that. And then we take, we do it in a sort of a cross multiplication kind of way. So I take 1 and multiply by negative 1. So it's 1 times negative 1. All right, so I take that product and I subtract this diagonal here, negative 2 times 3. Negative 2 times 3. So I'll just bracket each of those so you can see what's happened there. So I've removed the top row so that each time I've just got 4 to deal with. 1 times negative 1, subtract negative 2 times 3, in that sort of way. I'll just remove those markings. Okay, so the next row, so I'm just going to remove, I can't do that. I'll just try and remove them without removing the numbers, but I failed. Okay, the next row, we remove the middle line, and remember this is always going to look like this because we're only dealing in 3x3s, 3-dimensional vectors. So I now remove the middle row, and what I kind of want to do is go 3 times negative 1, except on the middle row we go in the opposite order. So we go these two first, so it's 2 times negative 2, subtract, and then that pair there, 3 times negative 1, 3 times negative 1. So that will be my y component. And so I'll just remove those lines very carefully. Lost my bracket. There we are. Now, finally, we remove our bottom row and we go back to how we started. So now it is back to 3 times 3. And we subtract this product here, 1 times 2. So this just gets us our cross product, which is a vector. So let's now calculate. I'll just remove these lines. Remove numbers as well, which was a bit careless. Negative 2, wasn't it there? And negative 1 here. Okay, so what have we got? We just need to calculate this out now. 1 times negative 1, so we've got minus 1 subtract negative 6. In the middle row, we've got negative 4 subtract negative 3. And the bottom row, we've got 9 subtract 2. So we're almost there. We have -1 subtract -6, so -1 plus 6 is 5. -4 subtract -3, so -4 plus 3, -1. 9 minus 2 is 7. There is our cross product. Now that is a vector. So this vector, so what this represents is a vector that is orthogonal. Orthogonal, or normal is another way of saying it's perpendicular. Orthogonal, normal, to A and B, to both A and B, right? Vectors A and vector B. So it's orthogonal to those. Now, we have a and the magnitude of A times B will be equal to 25, 26 and 49 square root of 75, or 5 root 3. And so the unit vector would be 1 over 5 root 3 in that direction, the normal unit. And so there we have it. That's our normal vector. Very important result, very important tool for us to have, very powerful, because it gives us the vector that is perpendicular to two known vectors, which we will find enables us to find the equation of a plane in 3D. So this is going to be very useful to us. Now, is there anything else I need to go through with you? Now, if this is true, we've got a vector here that's orthogonal to A and B. So what that should mean is I should be able to take this vector, I should be able to dot it with either one of these, either A or B, and I should get, what should I get? If I dot product two vectors that I know are perpendicular, I should get 0. Let's test it out. So let's test B against, so A times B, the vector A times B, right, dotted with B, the vector B, that should be equal to 0. Let's check it. So it's 5, -1, 7. Let's dot that with, didn't matter, with 2, 3, -1. And let's see what we get. 5 times we get 10, -3, -7, and lo and behold, I get 0. Isn't it beautiful when things work out? Okay, I think we can be doing exercise 11L, possibly maybe questions 1 to 5. So exercise 11L, questions 1 to 5.